Okay, so what I have in mind then is using this theory, which is actually very much a big part of the course. Kind of makes you appreciate appreciate calculus, and that is optimization. That is derivative becomes a big important shortcut of in optimization problems. So I didn't go all the way to actually to make that point very strongly with starting with this problem. Sometimes there's time. It is actually a good exercise to imagine yourself a farmer, okay, and try this problem. If you don't, not only you don't know calculus, you don't know really high school mathematics either. Okay, so the problem is really simple enough, and you might try to guess it, but suppose you are not guessing and you want to be sure, then how would you address that question? And that would actually require quite a lot of work, right? So so not building the enclosure itself, that's what I'm talking about, but you'd have to actually on a piece of paper imagine different width versus depth, and for each of them so that they would end up to 100 feet or yards of fencing, and then for different combination with depth, compute the area and then compare. Okay, so if you have a computer, you can use a spreadsheet, so that's actually not that bad once you do it, but it is trial and error pretty much. And it certainly totally works out if you know how to use Excel. You can not only you can have all the data, you can plot it, and that really suggests what can happen. But once you go beyond the why we don't stop there, and we don't really solve problem in that manner, because there will be more parameters, there will be more variables, there will be more data, and will be more at stake. So suppose you're optimizing a portfolio that is worth $50 billion, then trial and error is really not the way to go, and you have to be sure that there is a dip somewhere in the middle of your graph, and the Excel only gives you graph that is made of dots, so you have to make sure that there is no dip there, and then you are missing, maybe you might lose a couple of $1 billion that way. So that's why we proceed in this direction, and try to rely on something very ultimately simple, the derivative, to find the optimization, and instead of considering all infinitely many points on the graph of the function, okay, where is the maximum point? You have to, well, once you found it, you think you found, you still have to compare it to all possible candidates, okay, and there are infinitely many of them. So, but with derivative, the problem becomes much more tractable. So, so then the idea is to apply this theorem. Let me just run out through one example. Well, here's an example. So f of x is equal to, no, that's not the right one. Well, let's do this one, sin x. Okay, sin x. Define on the whole. I don't want to limit the domain just yet. So sin x defined on the whole line, and we certainly know enough about trig functions to know that it is between -1 and 1. But to confirm that, we can go with f prime of x, and it will be cosine x, and then to find what we call the critical points in other words, the ones with f prime of x equal to 0, what you end up with is an equation. And you shouldn't, however, like in those examples, assume that it will necessarily be some kind of quadratic polynomial. So this is a typical example, cosine x equal to 0. That is our equation that for each x satisfy this equation, cosine x equal to 0. And then you just look at it. Once again, the knowledge of trigonometry is necessary. But if you have a circle, once again, you draw that unit circle of yours, of ours that we use it all the time. So x is the angle, and then you just ask yourself under what circumstances cosine x is equal to 0, and x is equal to pi over 2 plus on and on plus 2, well, actually, k pi. Okay, so it will be either the first two will be one vertical and two vertical ones, but one up and one down, and then every pi you have more and more points of those. And that tells you, notice that how you the extreme points are unspecified. So among these, it's a whole list of values. So like this. So it will be pi over 2, 3 pi over 2, what is it, 5 pi over 2, and so on. Okay, so they includes both maximum and minimum points. Okay, so once you figure it out, then okay, that's I'm sorry, there is no pi over 2 there, like this. This is the answer. So the values are actually 0 pi, 0 pi, 2 pi, 3 pi, so pi at a time, and negative pi. Okay, so the angle is what we're looking at is in fact the cosine. So the function is sine. We're studying through its derivative, which is cosine, and we're looking at what its projection on the. No, I actually was right, wasn't I? No, hold on a second. Cosine equal. Hold on, what did I was right. Yeah, so I was right. Pi over 2 sine pi over 2, right? That's the maximum minimum point. So okay, but back to I don't know what the hell is wrong with me. Okay, so it alternates. We know that it alternates maximum minimum points, but the point is that it does not tell you. It does not tell you what is that which ones are maximum and which one are minimum. It does not tell you, because there is really no, for the derivative, there is no way of telling which one is the one on the left or one on the right. They look exactly, well, if you zoom in, it looks exactly the same. It's the tangent line is horizontal, so and that's all we know about the function. So in this particular case, then you need an extra examination to find out which one's which, but that's not really that bad, because what you do is you take those values for x, okay, pi over 2, 3 pi over 2, and then you plug them in, but not in the derivative, but in the original function. So f of x, you plug in pi over 2 into cosine, which is 1, and then it is 0, 5 pi over 2 is, I'm sorry, not 0, it's negative 1, and on and so on. You go with 1, negative 1, negative 1. So that is the plan that we're going to pursue. So once again, the setting the derivative equal to 0, that will be repeated many times, right? Solving that equation to the best of our ability, and then the result is of this solution is always the same. It is a list of values of x. So in fact, like this is what these are the critical points. Okay, so and then from each critical point we proceed to evaluate the function. Okay, and then what do we do with these? Look, the one that will be larger than others, and so we pretty much rank these. Rank these with the smaller, larger, and these are repetitive, and we know then the ones will be maximum and minimum, and each one will be maximum, and each negative one will be minimum. Okay, so that's roughly what we're going to be doing. So I'll do next the optimization problem, but let me take this out of the way, the question of the converse. So zero derivative doesn't mean maximum or minimum. Doesn't mean that you cannot conclude just because you have the zero derivative does not, well, pretty much doesn't say to you anything but the fact that the derivative is equal to 0. So the example is, of course, the x cubed function, which at 0 has a tangent line, which is 0, okay? And it's not a maximum or minimum. So this is the standard example. That should be on your mind. Just like you should remember, so function that is continuous but not differentiable. You should have an example. Something, or what else? And this is another one. The function derivative is equal to 0, but it's not a maximum point, something like that. So exceptions from rules. Or rules, there is now no exception from rules, but rather the rules that are easy to infer, but they are not actually rules. So that would be zero derivative implies that there is that point counts in some way is really not a rule. And that's not as much as an exception as it is a counterexample to that perceived rule. Counterexample meaning that it is an example of doesn't matter how simple that example is, if it is something that does not satisfy your rule, it means that there is no rule. Okay, so that kind of idea that exceptions prove the rule or something like that doesn't really apply, even though if I understand that expression correctly, it sort of means that if you point out, if you see an exception from the rule, if you see a statement which makes some point about something specific, then you assume that there is a rule that there is a rule, and this statement, such as a street sign, for example, is an exception from that rule. For example, if there is a parking sign, it means that elsewhere parking is prohibited, but if there's a sign parking, then so you see a parking sign, not only you infer that you can park here, but you also infer that you cannot park anywhere else. Otherwise they wouldn't put a sign there. The opposite, if you see a sign no parking, it means that not only you infer that you cannot park here, it means that you can park everywhere else where there is no sign. So there is an implicit rule, and you discover it by looking at exceptions. So that happens sometimes in mathematics, even though we try to be more precise that way, and so not rely on the unspoken things. Okay, so in this particular case, as you can see, we have the theorem is stated, and it is unambiguous. In fact, I think I can make a case for interpreting this theorem as that exception proves the rule, or rather points out at a rule. If I was to say that these two things are equivalent, derivative equal to 0 and maximum minimum point, I would have said so. Okay, because mathematicians try to make any statement as strong as possible. So if I can say that two things are the same, if there is a converse of a theorem, I would rather state it right there on the spot, even though it's not really, I wish it was the case, but really in reality, think about the Pythagorean theorem. The Pythagorean theorem says that, what does it say? It says that if you have a right triangle with sides A, B, C, okay, and the right triangle, the right angle is opposite of C. Okay, so that's a statement, and then the conclusion is that a squared plus b squared is equal to c squared. So that's the Pythagorean theorem, and that's how it is stated. Unless you forget about the build-up altogether, this is how the theorem is stated, at least. But the converse is also true. So even though it is stated as it is actually you can go either way. So if you have a triangle with sides ABC, which satisfy the equation on the right, you can say that that's the right triangle. And you know that the right angle will be the one opposite to side C. Okay, so it goes both ways. So this is the converse. So from left to right, one statement, converse from right to left. Conclusions, if it's once again an if-then statement, and which part is if, which one part is then, is the essence of the theorem. But sometimes you can flip them and it's still true. Okay, so that's called the converse. So it's true with the Pythagorean theorem. The converse is true for the Pythagorean theorem, but not for Fermat's theorem. So that function that we're looking at, counterexample, indicates that the converse is not true. The converse of Fermat's theorem is not true. So one little example, very simple function, probably one of the simplest one, and we have demonstrated that the converse is not true. Okay, so I want to do one more example of optimization, which requires more work than before. So where's that problem? Oh, here it is. We want to make the largest possible box from 10 by 10 piece of cardboard. Okay? Yes, and box meaning open box. Okay, so indeed that's the idea. If you want to make a picture, cut out the corners, right, and fold it and make a box. Okay, so we are in a similar place as with the problem of the enclosure for the farmer. So we have to make sense it first. So we have to be specific about what we mean by well, for one the largest. What are the variables? What?
Greatest volume.
Greatest volume. So maximize the volume of the box. Okay, and that is the output. What about the inputs? So the box. Where is the variability of the box? Because you could make different boxes from the same piece of cardboard depending on how large you cut out. The pieces of at the corners, right? So you can go either so how do we do it? No, let's make a box. So the box will look like this, right? Open box. It will look like this. Okay. So then these sides become the height of the box. But that's the result of the cutting will be the box. So what is the parameter? There's only one variability, because the box is, because it has to be a box, the height of each of the flaps that we're cutting from the square should have the same height. Okay, so let's call it x. So let x, so that's a word that is common, very convenient in mathematics too, when you're introducing a variable especially, or a function. So you have to be specific here, an affirmative, because there is no variable up until this point. There is no variable, and so you are solving the problem and you introducing the variable. So it is your kind of responsibility to say that to begin with, and then follow on to explain what that is. So let x be, how do we describe it?
That'd be the length of one side, wouldn't it?
Length of side of what?
Either the folded box or the cut.
Right, so
It's the same thing.
it is the same thing. So I would rather, so okay, we could have both descriptions to which explains things. So let x be the height of the box first, or which is the same thing, the side of the cutout square. Right, so this is x. Each of these is x. Right? So because all of these become vertical and they give you the height of the new box. Okay? So that's the setup. This is pretty much the description, almost entirely mathematical, even though I probably would then introduce the one more variable, v, for the volume. Right? So
X cubed.
that's right. So okay, so we're proceeding on to write the formula. So maximize v equal x cubed, and then subject to usually to restrictions. No, hold on. Why is it? It's not x cubed. Hold on a second. It's not x cubed. What's the volume? It's the height is x. The height is x. What's the other dimensions? This is x. What about this?
Length and width.
Yeah, what are they? So this is x times width and depth. Width times depth. Okay. So we will have only one variable, right? If we choose x to begin with, then we know how much we cut out, which means that the whole box is determined, which means that we should be able to express w and d in terms of x. Okay, so just look at the picture, the first picture, not the second, the first picture. Let's identify where they are. So, for example, depth. I think this is the depth, and say this is the width. Okay, so what are they? This is supposed to be red. Red.
10 minus 2x.
10 minus 2x, in both of them are 10 minus 2x. Right. And well, that's it. So we could have make it slightly longer solution, longer transition to this. If we would stop here, and then we would write a relation between w and d, and it would have taken it slightly longer, but ultimately it's the same solution. We just were able to skip through it quicker, and we end up with, so we have a function of x, which is, so find maximum value, point and value of a function f of x, which is x 10 minus 2x squared. Okay, just in case we could impose an restriction that x larger than or equal to 0, so that we wouldn't have anything weird going on. Okay, but otherwise this is a translation of our problem. As you can see, what's in the box is not has nothing to do with the has nothing to do with the geometry or the word problem we started with. This is it. And we have a function of one variable. You can plot it if you like and solve it. We usually plot it only as a confirmation of the result, even though it just as well you can start with the plotting, especially plotting. If the function is simple enough and you have a plotting instrument somewhere, you plot it and then you confirm your results. Okay, so that's one. Plot, then confirm, or confirm results with the Fermat's theorem. Okay, so that's one way. Or you start Fermat's theorem, find max, confirm with plotting. Okay, so either way, let's do. I think let's do Fermat theorem first. So we'll just go in an entirely detached algebraic way. We'll just do differentiation. So let's be specific here. The function is differentiable. Why is the function differentiable? How do we know it's differentiable?
Because we can always cut off more, get smaller and smaller.
No, we're detached. Differentiable. What's the differentiability? Differentiability means that there is the derivative. How do we know that this function has the derivative? What's so special about this function? What's so nice about this function?
Continuous.
Not every continuous function is differentiable to begin with. But vice versa is true. So every differentiable function is continuous. So what's so nice about this function? The answer is the same. It's a polynomial. Polynomials are not only continuous; they are differentiables for sure as well. So it's a polynomial, and then that's why we are justified applying the Fermat theorem, so that we could now use the derivative. So it's differentiable at every single point, so it has a derivative, and then the local max points satisfy by Fermat's theorem satisfy v prime of x equals 0. Okay, so that's the explanation of what we're doing. This is how the theorem is invoked. So the function is differentiable. Well, let's take another look at the theorem. As you can see, the assumptions are the function is differentiable, and secondly, we're looking at a point which is an extreme point. So at this point, we're not trying to look for the maximum. That comes later. We're just looking for extreme points, and also known as critical points. So this is, in other words, it's a critical point. A critical point, derivative equal to 0. Okay, so we're justified then differentiating and doing algebra as just as last time. So compute the derivative v prime of x equal to, at this point, so I am to differentiate x times 10 minus 2x squared, like this. Okay, so at this time it is up to you to decide which way you prefer to differentiate, and it might depend on your whatever has been, how you have been doing it recently, and methods that you prefer. So how would you do it?
You gotta do the product rule.
Product rule. So product rule is a possibility. There might be an easier way. I mean, once again, as I said, it's not necessarily if you choose your tool. It might be because it is indeed the easiest for you. But there are other ways that.
You can go ahead and expand it too.
That's right. The expanding is actually, I think personally, is easier. Yeah. So expand, and then you don't need the product rule, right? So you do more algebra of the usual way. So x, I expand this, 10 squared minus 2 times 2 times 10 times 2 times x plus 2x squared prime. Okay, so what I'm ending up with is 100x minus, what do I have here, 40? 40x and plus 4x squared. Okay? So and then prime. Okay, so we still need to find the derivative of this. So simplification of a function, as you can see, it depends on the context. We are making functions simpler for differentiation, even though under different circumstances, maybe we want something else from the function, we would do something else. So, the function is factored. Remember, when the function is factored, it gives you some information about the graph. For example, we can see right away the x-intercepts. What are the x-intercepts of this function? X-intercepts? 0, yes, true. And there is another one?
5.
And 5. So the factors, each factor gives you an x-intercept. Okay? So incidentally, so these are 2 x-intercepts. If we will revisit this later. Let's just run through the Fermat's theorem first. Okay, so differentiation now is easy. We're applying just as we always have done with the polynomials. We differentiate, we split it into components and differentiate it one at a time. So the derivative of the first component, or first term, 100x, what's the derivative? I'm sorry, I think I missed over here squared over here. Okay, and this is cubed. I forgot. Sorry. So 2x squared, 4x squared times x. Okay. So derivative of 100x is 100, and the next one is 80x and 12x squared. Okay, so that's the derivative. So we found the derivative, and we return to our equation, Fermat's theorem equation, and we have to solve it. So we set it equal to 0 and solve. Okay, so it is a quadratic equation, so that shouldn't be any trouble. So let me write it out. Solve 12x squared minus 80x plus 100 equal to 0. I could simplify. I mean, the quadratic equation can be solved at any moment of time if you have your quadratic formula available. Okay, but it does make sense. I think I will divide it like by what? By 4. Yeah, I divide by 4, so make it simpler. So divide by 4, have 3x squared minus 20x plus 25 equal to 0. And now I apply the quadratic formula. I mean, it's once again, the tool is yours, so if you know how to easily factor, some people are amazing at that, so you just factor it and then you have your answer. I personally prefer just go straight to the quadratic formula. So x is equal to, remember the formula? Negative b. Okay, so this is my b, negative 20. Okay, so I will start with 20 plus or minus square root of
b squared minus 4ac.
That's right. So b squared, which is negative 20 squared minus 4ac, which is 4 times a times c, 25. So this is c and this is a, and divided by 2a. All right. So what do we have? 20 plus or minus. And here I have 400 minus 300. Okay, so divided by 6. And I have 20 plus or minus square root of 100, which is 10, over 6. And I have two answers. 30 divided by 6, which is 5. And 10 by 6, which is 2, 3, yeah, yeah. No, I want to keep fractions, so let me put it this way, and 5/3. Right. Okay. Okay. So which way we ahead of time we don't know. So both of them are potential maximum points. So what do we do? So list critical points and compare. So I'll just take these two. No, I'll put 0 just in case, because 0 is the end point of our well, actually, if you want to be careful, the restriction is that the length, the cutout square has the width of x, which cannot be negative, so that's the restriction I put up there. But I could also require that x cannot be larger than, what is it? So it's 10 by 10, so it cannot be larger than 5, right? X cannot be actually larger than 5. Okay, so that's convenient for us. So I'll put 0 here, 5/3, and 5. So these are the x's, the critical points, and then I compute f of x, which is our polynomial, not the v of x, I'm sorry, v of x, which is not, once again, commonly made mistake if you just doing it too fast. A common mistake is to look at the very last formula that you just used, and that is the derivative, so you have to actually go all the way back to the original function v and substitute into that formula. And the fact that it's factored is actually convenient. So I have to compute x, 10 minus 2x squared. The fact that it is factored makes it easy to compute by hand. So v of 0 is 0 times something, so it is 0. So naturally, think about it. If you cut out, you don't cut out anything, right? So if you don't cut out anything at the corners, then the height of your box is 0, the volume is 0. Okay, that makes sense. Now if I put 5/3 here, it is 5/3, 10 minus 5/3, so 10/3, and so what squared. What does it give us? 5/3, and is it 6? So 30 minus 10, so 20/3. Right, so your common denominators will be 30 over 3 minus 10 over 3, so it's 20 over 3. Okay, so which gives me 100/9, right? Okay, so at least I think it is correct. Okay, so and now v of 5 is 5, 10 minus 2 times 5 squared, and the second term is 0, so it is 0. So these are the three numbers for us to compare: 0, 10/9, and another 0. So this is the max, right? And these will be it is technically this is a local maximum, but that's where derivative is equal to 0. But since the list, so if we just stop, I maybe rush too quickly through this. Let's make sure that what we have discovered by the Fermat's theorem, this is what we have discovered. So let me say this. So these are candidates for global max min. So according to the Fermat's theorem, it is if you have a local max min, then it is on the list. But every global max or minimum point is also local. Okay, so which means that we have a list, maybe excessively long list, but it is a list that includes all candidates. Okay, so these are the candidates, and now how do we choose best? And then depending on what you're looking for, the best will be either the largest or the smallest. And now we finally compare these three values. We discover the largest one. So the conclusion is the max of V is 100/9 attained at the point x equal to 5/3. Okay? To confirm, it is really, once we have these numbers, it is very easy to confirm even without any kind of graphic capability. This is very easy. You can see, look at these three numbers. What does the graph look like? Well, like I said, you don't need graphic capabilities to look at it. It is, the value is 0 at 0. Let me just take these 3 points and plot them. One is here. The one is there at 5, the last one, and then somewhere in the middle is a larger value. Okay, so and there are no other. The key is there are no other extreme points. So there are no dips anymore. So it goes straight here and straight there roughly. The only thing that is you can also gain from this is on right, what's happening on right. These are two x-intercepts and the only two x-intercepts. But what's happening at 5? What is happening at 5? Not only it is the x-intercept, but also what else is it also? Derivative equal to 0. So what does it do there? It touches the x-axis like this. Okay, so all the information is actually already here. We don't have to go anywhere to plot it, and that pretty much that's just a confirmation. This is certainly the answer is right here. So that's the answer. Well, the answer, technically, you should put the answer in the language of the original problem. So the answer would be the maximum box is 100/9. Whatever units, square units, and it is if you cut out squares 5/3 by 5/3. Okay, so that's technically what the answer should be to the original problem. But also we get extra information. Rather, what we did next, we confirmed the answer by sort of deriving the shape of the graph from the information that we had. And now I want to show you that we could have derived this information from the very early situation. That's here. Look at it. It is a cubic polynomial, and it immediately we know that there are two x-intercepts, 0 and 5. Okay, so 0 and 5. So let me do it. So let's pretend that we don't know. So then I am plotting right away 2 points here and there. Okay, and then can you justify the graph from this information only? So the graph looks like this. Can you justify it? A cubic polynomial with 2 x-intercepts. So why doesn't it go like this?
Because anything greater than 5, it gives it infinity.
Well, that's right. You could put it in a more precise way, in a more precise shape is meaning that you would say the limit. What you just said, you just didn't use the word limit, but indeed this function goes to this one, goes to infinity as x goes to infinity, to plus infinity. Okay, so it's a cubic, and has negative infinity on one end and positive infinity on the other end. So it means that when it when it reaches the x-axis at 5, it cannot go down and cross it. Because, why not? Because then how does it go back to infinity? It would have to cross the x-axis again, and we know that it does not, right? Here we refer to another result which is the intermediate value theorem, which says that if you're below the x-axis, function is continuous, you got to get on the other side of the x-axis, you got to cross it at some point. So, which means that this possibility is out of the question, and then we know that to the left of 0 everything is negative, to the right of 5 everything is positive, and between 0 and 5 we have this dome, which means that we could have guessed without going through all the derivative, that the maximum is here somewhere between 0 and 5. Okay, the only problem is there's no symmetry, and would not, best guess would have been to say 5, right? I'm sorry, 5 over 2.5. That would have been our best guess, that this is 2.5. Because if we assume symmetry. But the result is certainly slightly off, and so it is 5/3. Yeah, so it's slightly larger than 1/4. Than 2.5. No, wait a minute, it's slightly smaller. Yeah, it's slightly small. Okay, so that's how this is a typical problem of how we run through the whole thing. Okay, so not to worry about the upcoming tests. So this happens not gonna be on the test. The only problem you might be still asked to sort of do the initial part. This is a fairly long problem, and we try to study and especially evaluate whenever a test comes in one part at a time. So one part is to set up the problem, translate it like this. The second one to translate it all the way into a calculus problem, which is this one. Okay, and then actually carrying out the rest of the problem, and then we try to evaluate differentiation separately and test for differentiation separately. So like I said, this part might come up on the test. This part. But other than that, we usually just you usually get a function. So you are starting here. So you differentiate, and then you run through these steps to solve the rest of the problem. Okay, so a bunch of optimization problems are online as well as on the in the book or elsewhere. Okay, so something that did come up a couple of times, and we just have to be more specific here. The clock is ahead by a few minutes. It is the limiting the domain. Remember, limiting the domain adds the endpoints into consideration. Okay, so usually you look at the critical points and where the derivative is equal to 0, and that's the list. Okay, so it just happened here that the nature of the problems dictates the interval of x, which makes sense, and that's how we ended up with 0 over here. The beginning and the end, not this 0, but rather this 0 over here. The beginning of and the ending of the interval of reasonable values for x. X being the cutout thing, so which means that it has to be positive, and you cannot cut out more than half of the square. Okay, so that's why it has to be between 0 and 5, and that's why I added these two to the list. These two to the list. So we have two critical points, derivative equal to 0, 1 and 2. So those two come in immediately, and then you have to add the endpoints, because they're still candidates. The example is that is, I showed you before. Let's, well, this could be, so if this is your function, okay, then this might be your interval, and then look at it, what happens around this interval. The actual max is here, okay, and the actual minimum is there. So which means that the critical points, even though that's how you would proceed doing it, the two critical points that you'll find, they are not the ones. So if they look interesting, they have a horizontal tangent line. The endpoints don't have that, but they have to be on the list so that you, because that is the practically speaking, the highest value is the maximum, and it just happens to be at the endpoint. It could also happen if we take our function x cubed. That is especially a simple example of this situation. So my graph looks like this, and what if I am to maximize on -1, 2? Okay, so then -1, and this is 2. So I run through my steps. I take f prime of x is equal to 2x. 3x squared. I set it equal to 0 and solve. Okay, then I conclude that x equal to 0 is the critical point. So and then I circle the points to be considered. So these are 3 values to put on the list to compare. Remember that's the point of the list, is to compare. These are candidates. So candidates, that's so they are the values of x. They're -1, 0, 2, and then x cubed is computed, gives me -1, 0, 8, and then this will be the max, and this will be the min, and this one is nothing. Okay. All right. So tomorrow the test. So anything else you want to ask about it?
It's probably not going to be